En esta sesión del seminario organizado por el Grupo de Investigación en Didáctica de las Matemáticas del IUMA de la Universidad de Zaragoza, el doctor Sacchet de la Universidad de Turín muestra una actividad realizada con estudiantes universitarios utilizando una herramienta de generación y evaluación automática de ejemplos en el contexto de la factorización de polinomios.
Just to say something a little bit more about myself, I am from the University of Torino. So now, more or less, all of you already know it, but for those of you who doesn't know it, let's say it's a university in Italy, in the northwest of the country. And as a department in the university, I am in the biotechnology department, which looks quite strange, but there is a group working in mathematics education even there. So there's this is a multidisciplinary department, so there are people from several areas and also the mathematicians, let's say, and part of it in education. So today I will try to make a short presentation of a research, of one of the research items that we carry on about the usage of automatic assessment system in order to evaluate something more complex from the cognitive point of view from students. So trying to evaluate conceptual understanding of students, especially using a technique which is the one of making students generate examples of some mathematical concept, let's say, that satisfy some constraint and so on. It's something that say mathematicians typically do, like providing counterexamples for a theorem, or let's say in some way showing how much the hypothesis of your theorem can be pushed in a certain direction, but after a while, I provide an example, no more than that can be done. Okay? So we are not going to let students work on such high level of mathematical, say, working on proving theorem, let's say. This is an activity that we carried on with STEM students, so non-mathematicians. Something a little bit more that some of you may already know, but so this is the, let's say, my research group, which is called Delta Research Group. Delta stands for Digital Education for Teaching and Learning Advances. So we work with digital education in a very large sense, but then most of the people in here are mathematicians, so we focus a lot on the exploration of the teaching and learning mathematics using digital technologies. Okay, so coming to the topic of this seminar. So how can we join the automatic assessment with the assessment, let's say, of advanced mathematical competencies? One of the things that, I don't know, usually it's not so radicated into educators' mind is that, okay, it's possible to use automatic assessment, even very simple systems, in order to assess or to make students develop mathematical competencies and, let's say, also a little bit advanced sometimes. So this is the first item, so it's not coming just for us, but also from other examples in the literature. Also, on the other side, so we try to join this pedagogical approach that I was telling you before of generating the example generation by the students, which is something really that has also been shown in literature to be effective for mathematical understanding of concepts. And also, in this research, we made it something like intercultural, because we joined the experience of two universities. We have some contacts with a Swedish university in Karlstad, and we wanted also to understand how was the difference from the cultural point of view, but not only also the educational context in the university or in the country, let's say, in two different countries. The two countries, of course, have, I don't know, several point in common, we try to analyze them before, and also several differences in the background of the students. But I will tell you something in a while about the background in the two nations, let's say. But first, let me tell you what were the research questions that were pushing this research. So, one of the questions is how this technique of example generating task can affect students' example space. You can think of students that they have a certain, let's say, set in which they can collect their example that can provide, but how can this be enlarged a little bit in order to have students open a little bit more their mind on the possibilities around the mathematical concept. And also, after this experience, and also in the meanwhile, we were working with the students, we try to understand what are good design principles for items, assessment items, in order to be useful to foster these competencies, of course, with the support of computer-aided assessment. About the background of the two countries, let's say. So starting with the Swedish one, in this case, the sample that we consider is given by first-year engineering students, and our counterpart, the other researcher in the Swedish university, were able to involve 200 students, around 200 students. And in their module, of course, there are differences also in the module that is to which the student attend, because they are engineers. Our other students, I will tell you in a while. So, but just to tell you also some topics, because these are the ones in which we focus our research. They deal with elementary functions, so function in general, properties, factoring, the factor theorem, and so on. So they work on also several registering of representation, like algebraic, geometric, and analytic representation of functions. And just for you to know the context, the research that so the activities that were carried out in Sweden were made compulsory for the students in order to, for the examination, so they had to do it. This was from the point of view of the sample in Sweden, but also we needed to understand what is the background of the students. They were first year, so they just started university. We could not expect them to be already university students. They are more secondary students. That's why we also investigated what is the background, so what is the expected mathematical knowledge, competencies after secondary education in Sweden. Of course, there is it's mentioning the algebraic and graphical representation of function. There is a method for solving quadratic equations. I will come into this a little bit later. Also, properties of functions that are polynomials, and method for solving polynomial equation, and also the factorization. So these are all the elements that were part in the task that we proposed to the students, and they are in some way all cited in the Swedish secondary school background. On the other side, in Italy, of course, we were involving first-year students in the biotechnology degree program. That's one of my department degree programs. We have a module which is mathematics and biostatistics with computer application, let's say. And in this case, we have less than 200 students than the Swedish one, because the maximum amount is a closed environment, let's say, no more than 160 first-year students we can have. And we were making this activity optional, because we had already a specific program, so we want them to choose whether they want to do something more or not, even if we suggest them, okay, it's useful for your preparation, so don't be afraid of it. But we made it optional, so we have 111, so around 100 students that were carrying out this activity. So globally, our sample size is around 300 students, which is quite okay. And in our module, we cover again, similar topics, maybe with differences, of course. The professors are different. The context, so engineers, maybe they need a little bit more mathematics with respect to biotechnology, biotechnologies, but they need that anyway. But we cover anyway elementary function, transformation. Usually we made a lot of manipulation of graphics in order to make them visualize the mathematical concepts. This is a teaching strategy, let's say. Also including translation, dilation, and scaling of graphics. We make a little bit less algebraic computation or factorization because it's not our aim. So our aim is that they are able to understand the mathematics that is behind it, but not to make such calculation. We use computer-aided application in order to let them be eased by calculations, let's say. But generally, anyway, these are students like, we can think of them really as generic secondary students as the whole context, so we understand also what is the preparation after secondary school. And of course we have similar topics, maybe expressed a little bit differently depending on the guidelines of the local ministries, let's say. Anyway, we have solving linear system, which is quite important also for the activity, polynomial factorization, polynomial manipulation, and also from the point of view of functions, representation, especially of functions with degree 1 or 2. And also, since it's the Italian one, we know a little bit more about it. Also, we were able to divide a little bit more about the grade of the students. Speaking about analytical and graphical study of the main kinds of functions, the concept of zero, and solutions of polynomial equations. It's something like quite standard that everybody more or less can expect from secondary school students. Okay, now I'm almost going to the tasks that we propose to the students. Just to mention what are the main mathematical concepts behind theorem, behind the tasks that we propose to the students. One is the so-called factor theorem. In Italy we call it Ruffini's theorem. I don't know how you call it. Okay, Ruffini. Anyway, this is quite a well-known. You have a root of a polynomial. If and only if it is divisible by x minus that root, let's say. Okay, then this theorem, for the point of view of the example generation, has a direct application. If I want to provide an example of a polynomial that contains a certain root, I just need this one to be a factor of my polynomial. Very easy application of the factor theorem. Another tool that students were using while carrying out the task is the manipulation of graphics, as I was telling you before, in order, for example, to make the function, like this parabola, passing through a certain point. I have this parabola here. I will make it not just to pass from 0 minus 1, but it's 2. I want to pass the function to pass to 2, 3.5, but here is for 2 and 3. I need to multiply by 1/2 in order to have the representation, keeping the zeros fixed. So it's, the task is about manipulation of the zeros and points that a polynomial contains. So this is one of the several tasks that we propose to the students. I say one-off because we have a lot of tasks about asymptotes, about calculus, about other things, but the first analysis, the research, we made it on this one. So we have 4 properties of a polynomial. The first one is the polynomial to be of degree 3. The second and the third one is to contain a specific root, usually a different one. A and B are automatically generated parameters by the assessment system. And the last one is that the polynomial evaluated in 0, so the last term of the polynomial must be minus 2ab, where ab are the same roots as before. Then, very easily, the task asks the students to give an example of a polynomial that satisfies, and the property were, in the meanwhile, added to the... so, the first one contains just the first property, the second item contains the first and the second property, and so on. The last one contains all the properties, And we added also another example in order to, as I was telling you before, expanding the example space of students. We are skipping the degree polynomial number 3 and making them go beyond their the problem, using more degrees of variation of their example space. Okay, so it's explicitly written, but not the first property. So then students were working, so at least in our case, we make students work in groups. And usually in these activities we had several tasks that were common, so for all groups it was equal, and some tasks that were different, so they were automatically generated parameters, so even each member of the group have different parameters, and they need to confront each other in order to understand a suitable strategy in order to solve the task. Usually also we ask students to justify their answer in order to collect more data for our research to understand what was their reasoning behind this calculation, example generation, let's say. Okay, I already mentioned the theorems behind it, so these were the main strategies that we found out, then I have more details about the data we collected. Of course, the factor theorem. Also the vertical scaling in order for property number 4, in order to make the function pass through 0 minus 2ab. The multiplication by a factor, of course, in order to reach the degree 3. And also, this is quite, I already anticipated to you, this is quite the one that Italian students like the most. So I have the generic expression of degree 3 polynomial. I make a system expressing some parameters, so p of 0 minus b equal to something. So okay, this parameter should, okay, and then adding the various constraints, I solve my system. When I have a free parameter, I put something randomly, and that's it. So, but the Italian students really like this this method, probably depending on how it is taught also in secondary schools. Then we have some data, of course, that we try to collect about the various prompts. Okay, I skipped the first prompt, which is just giving an example of the degree 3 polynomial. It's just really for make them confident with try to something easy that they are able to solve quite easily, let's say. But it's also a strategy that we use quite a lot when making activities with students. We provide students with items that have increasing difficulty, more or less also in this example. And usually the first one are like more inclusive for everybody, let's say. But then, so there was nothing interesting in that first prompt. So let's start with the degree 3 polynomial with one root. Okay. And in this case, okay, it's a table full of quite a lot of numbers. Just to mention, also for the sake of interpretation, we try to here analyze the first column, analyze the various kind of responses that were given by the students. Together with the other researcher, we use some coding, let's say. We said, because, okay, there were sometimes some forms which were quite common, let's say, and some forms which are like, okay, I don't know why they choose it, but there are students who choose this like really random parameters and there's no reason behind it. It's a little bit more difficult, like other or, okay, no answer, so of course, empty. Another classification that we use is this column here. We call in our, say, research activities, FF, like factor form, so the students provide the response using factors, say, while standard form, whatever standard means, we use this name, means just a polynomial written in the normal way which you write a polynomial, so x to the power 3 plus so on. Okay? Usually we notice that students are more accustomed with the standard form, even though in this case it was easier to use the factor form. But I don't know, probably also just a perception that they have, okay, the polynomial should be written in this way, there's no other way. So factor is not like a polynomial. even from the mathematical point of view, they are the same. Okay. Then we highlighted also some numbers in here, and in the next slide, of course, I try to explain why we have highlighted them. Of course, we have also a difference from the Karlstad University students, which is these two columns, and UNITO students, which are here. We mark the number of kind of responses, also with percentages, and also among these responses, which one were correct or not. They may have used a suitable form, like this one could be easy, or this one could be easy for this task, but they may have done it incorrectly. I don't know what they did actually. Maybe they just put x to the power 3 minus a, and that's it. I don't remember exactly the wrong ones, what they did. Anyway, the numbers highlighted in here, we wanted also, they want to highlight also our attempt to understand which were the strategies that were used by students. So how much do they use the factor theorem, or how much do they use other strategies? And for example, for the 50 students in Karlstad University, they used the factor form. So this one used the other one used the factor form. So we are pretty sure that these students use the factor theorem, the Ruffini theorem, because they wrote it explicitly in their answer without mentioning it, but with their response, we were pretty sure that they did it. Also, some Italian students, a little less, let's say. I don't know, this is cultural background, that was also part of the research. We're using this kind of theorem, even though the percentages could be, let's say, okay, remember that the global sample was of Italian students was half of the Swedish sample. So that's why we added also percentages in this representation. So in some cases we have the evidence of having used the factor theorem, but on the other side we have also some evidence for this first task of students that did not use the factor theorem, for example, using this first form here. And this first task was really quite simple. Now, so it's also quite normal that the factor theorem was not required. Let's say the easy examples can be done also without the factor theorem. Now let's go a little bit. I have also some graphics, but I don't remember. Okay, so in general, we have some clear indication from the answers of the students whether they use the factor theorem or not, but in this example, for a large amount of responses, it's not clear. They may have used it or they may not have used it. We are just adding the strategy to the students when it is explicitly clear in some way that the students have used it. And for this, we were not using just this task, we are also using other tasks responded by students. So, for example, in some other part of the assessment, they wrote about the factor theorem, we can say, okay, we are pretty sure that they may have used it also in this task here. Okay, and this is some recap of the findings. I just move also a little bit. Okay, it's easier to read it this way. That's one of the conclusions that we had. So this is not the conclusion of the presentation, but one of the conclusions from the first prompt, or second prompt, let's say, is that the Swedish students, also Karlstad students, were more using the factor theorem, while the Italian students instead prefer really solving a system of equation, even though in this case it's not so evident by now. Also, I was anticipating something in the previous slide. We made a comparison with another task in order to check the presence of the factor theorem. And, okay, for example, a lot of Karlstad students mentioned the factor theorem in another task. So that's why we are pretty confident about their usage. Moving on, let's say, to the third task. Oh, this is actually, from the point of view of the activity, since we had 300 students, it was automatically evaluated So we were using a software that, I told you something about to the students in the training module, but we use a software that allows also writing generic polynomial and then check substituting the right parameters if this polynomial is suitable or not, as an example, like checking if the zeros are there and so on. Okay. In this case, there is another task, so the table is really similar. I'm not describing it again. Now we're going to focus on the, I go back and forth one moment to focus on the colored circles, let's say. In this case, they have the two roots to find, let's say. And of course, again, as we have seen before, some students use the factor theorem, for example, 65 and 15 from UNITO, when they are writing the polynomial in factor form like this one. So adding x, the easiest way of adding, reaching degree 3 with the two roots, or adding another root general, so which is a quite standard way of generating examples. So there is more usage, but in this task it was a little bit forced the usage of this kind of strategy, let's say. But what about this one here? So the percentage, okay, this one here, which they wrote the polynomial in standard form. Okay, the work of the researcher was also to take the polynomial, factor it, and we used, of course, some tools for factorization, and check whether it was falling in another, in which one of the two categories was falling, or in another one. For example, even just adding a parameter at the beginning of x to the power cube was different to the other ones. Okay? So we needed to check also in which categories they were falling, and we had to do it. It was quite quite annoying, but it was useful to understand whether they used the factor theorem or not. But it was not sure. We have only some plausible inference that they may have used the factor form, okay? The factor theorem, sorry, because they mentioned it also in a previous task, okay? And in this case, we have students who answered that element in factorial in standard form, but for example, so this is also a graph of how many students in Karlstad and in Torino answered with this form, standard or factor. But we just in order to move to the next task, because they were subsequent one to each other, we need students to understand also. So usually students, what do they do? So also human, let's say. I have a generated example, I'm adding an hypothesis, I try to modify my previous example in order to satisfy also the other hypothesis. But in this case, we were let's say, teachers that were pushing also students to do something different, because with this example here, if you plug the 0, x equals 0 to the polynomial, you have that the function passes to 0, 0. So they cannot use the vertical scaling in order to make this polynomial here passes through the minus 2ab. So in this case, so this is just a constraint. They cannot use the previous generated example in order to modify it, or they need to modify it not with vertical scaling, with other means, let's say. It was just a remark because the Italian students were also using a lot vertical scaling due to the background also, their background and the module at the university. Okay, speaking about the prompt number D, okay, in which we have these constraints, about the possibilities, the main one that we categorize for this kind of task. We have, of course, these one here, like very similar, but just with a minus sign in order to make it right. This kind of polynomial, we're using vertical scaling, but with a different root, of course. The one that was the example of the previous slide, let's say. And and that's it, more or less. Okay. Oh, here there is also, I will not focus because in this case we were asking all properties from 1 to 4, and in the prompt we wrote 1-4. But students, they want to interpret also, this is another also cultural perspective, let's say. They wanted to interpret 1 and 4 because it's easier to find an example in that sense. So some of the students were providing an example just with of degree 3 with that with P of 0 equal to -2 AB. Okay? And in this case, of course, again, the percentage of using the factor form is again quite similar to the prompt C. This is the error impacting the individual students. And also, again, we have similar hypotheses on the usage of factor theorem in the previous task. So that's why also we have some little inference for this usage. And also, okay, we have, again, the percentages in here, in which a lot of Carsa students and some of the Utah students, but due to that mistake, let's say, answer this polynomial here in factor or in standard form. So this polynomial also, they answered it also in the previous task. So they already have the example for task number D. Okay, and okay, so what are the findings from this? So I'm going to the richer items, assessment items. About the use of vertical scaling, for example. Okay, we have we have students, of course, who use the vertical scaling, and we have the percentages in here. So okay, quite small, but for the UNITO students, the percentage is a little bit higher. Also, so to justify that Italian students prefer it a little bit more, say. And also we have other hypotheses, let's say, of having used vertical scaling. For example, when the answer given in prompt C was multiplied by the same factor, let me remember, but changing, okay, so only the intersection with the x-axis. So they may have used the vertical scaling because it's the same answer with just this factor more. We are not sure of it, of course. we have this adjustment from the researcher point of view. Okay. And the last item, this was also done. I tell you also what it was the philosophy behind this task. Last one was asking to provide 2 examples, not just one, of polynomial that satisfy the 3 properties, but not the first one of being degree 3. And of course, there is one simple answer, which is there is only one degree 2 polynomial that does it, but we ask for a second example in order to make them go also on the 4th degree polynomial. So that's why among the, it's a little bit blurry, but it's okay. On the possible responses, we have the only degree 2 polynomial that has these properties. On the other side, we have, of course, quadratic polynomials, so degree 4 polynomials, in different shapes. Like, for example, when having 2 roots of this way, I need to scale them. Or whenever I have a general degree 2 polynomial added in here, I need to adjust the factor in front of it again in order to scale the polynomial. Oh, then some people also added other kind of degree 4 polynomial. They did not fall into these 2 categories, or also going beyond the degree 4, but it's quite rare as an example. Okay, and in this case we have, say, 36% of Carter students and 12% of UTO students that answered at least one of the 2 examples. Say, some students were also not able to go beyond this set of possibilities, let's say. And these are, again, similar percentages of those who perform correctly in prompt C. And also, there are 40% of students, Carlson students, that answered in standard form, but mentioning the factor theory in the previous task. So again, it's plausible that they have used this kind of strategy. And again, what I was telling you before, this was we counted also how many people used the simplest polynomial, which is the degree 2. So this, it's okay, it was the only possibility. So we are not very sure about the use of a certain strategy beyond, say, how did they find it, let's say. We noticed that some students were using also vertical scaling in other examples, so it's again some plausible hypothesis that these percentages of students were using also vertical scaling even when creating this only example. And okay, I spoke a lot about percentages, about the various strategies. And in this case, we wanted also, so not just to provide this data, which was it took quite a lot of work to analyze these responses. Of course, the analysis was divided by Swedish researcher and Italian researchers, so everybody did their also for privacy of the students, let's say. And in general, really, we wanted to assess what are the strategies, but also to find some global observation beyond these specific examples on the task. One, I already anticipated something at the beginning, but one of the remarks is that the Swedish students were more suitable in using the factor theorem. This is also due to the fact that it was also algebraic representation are more taught in their university module and also explicit in the preparation before university. While on the other side, we use the flag even though we can say CASA student and students, so the university context is international, but just to provide some global background, let's say. We can think of, say, of Italian students that they tend to solve using, say, calculating parameters on the general expression of a polynomial. Also, students in CASA provided more correct answers. They were responding better. Okay, they are also engineers, so we may expect them also to behave a little bit better. And also the method that they use, it's very difficult to make a mistake while using this strategy, let's say. On the other side, the Italian students, also due to the topics that are done in the module of university module, they are a little bit invited maybe also to use the vertical scale. Something that was in common also, I already anticipated everything at the beginning, but knowing the research from start to end, I already told you before that students look like more comfortable in writing a polynomial explicitly in the standard form. Okay. They think of the factor formula as a kind of unnatural polynomial, probably. And also, the use of the various strategies increases also depending on the item. Okay? In the first one, there was just the roots. The factor theorem was really the easiest way. On the other side, in the last two items, we were also asking the polynomial to pass to a certain point, and with the use of this strategy was also encouraged. So globally, these results are quite interesting in order to understand really how the students think of their example spaces when working. Okay, it's almost time, just some minutes more. It was interesting to understand really how the students behave when dealing with example generating tasks, also for the conceptual understanding of factor theorem, of vertical scaling, of this kind of mathematical concepts. And in this case, also while working with this task and viewing the activity of the students, we were able to think of some design principles which are quite suitable for this kind of assessment, so computer-based, automatically evaluated with example generation. And also, say, thinking about not just technology, but also methodological, from a methodological point of view. For example, using a chain of prompts, so increasing difficulty, asking for more examples, helps to make students think of a larger example space. Also in some of the tasks, maybe not in this one, we try to use also immediate feedback. So for example, immediate feedback means really while doing the task. So it was not in this one, I'm pretty sure, but in another one, we provided students to the chance of writing, for example, a function or a polynomial and clicking a button to view the graph, so another representation of the element that they wrote in their answer, to check if the property was satisfied or not, graphically, for example. So really, it's an immediate feedback in the sense that it's while doing the task, not afterwards that I received it. So I have my assessment, I have the score, and I view my mistake, and I can check whether I did it correct or not, or change other forms and so on. So in general, the feedback is also trying to give it with a different register, different form, different, so with respect to what they write in the answer. So it's not I give you the response, but I give you the chance to reason a little bit more on that. Of course, also the interactivity, so being able to elaborate on the, in fact, students in this case, okay, for the CASTA students, where they were encouraged to use dynamic software while performing the task in order to try to explore what were the possibilities. In the Italian case, we made it a lot easier for the students. We embed something in the item, so it was easier, so it was already prepared for them to explore some of the concept behind the task. So again, this it's a little bit different, immediate with respect to interactive feedback. Interactive means that, okay, I have something that I can elaborate, that I can explore in order to find a suggestion on my answer to on the strategy that I can adopt. Okay, so the answers, where it can be plotted, for example, using dynamic geometry system was also encouraged. It's like an implicit feedback, let's say. And going to the end, also, we were trying also to pay attention to the cultural differences, adopting tasks to different backgrounds. So it's not so different, we can say it's European again, so we are in Europe, we don't have maybe so much differences, but we try also to be aware of that. And also another useful design principle, we took advantage of the computer capabilities in order to generate several examples, in order so that students did not focus on working together on the same parameters, on the same task, but they have different ones. They have to confront each other to find a strategy based not on the numbers that they have, but really on the context of the task, and discuss the results into groups. Then, okay, we have some slides about the research question, and this research is published in the International Journal of Research in Undergraduate Mathematics Education, and we have also some other references that I cited at the beginning, and I think it's quite okay to leave also some room for question, and thank you for your attention, of course.